out of 4 basic arithmetic operations, the next one that we have to cover is multiplication. So let's recall how we perform multiplication of two numbers using just standard college technique. So if we have numbers x0, x1 through xn minus 1, the binary representation of the first of them, and the representation of the second number, yn minus 1, then, well, independent actually of whether it is a binary or decimal representation, what we do, we compute the product of the first number by each of the digits of the second number, and then we add up the corresponding numbers. So the product of numbers is translated into sum of many other numbers. And for binary notation, this is especially simple because multiplication of a number by a single digit is either constant 0, well, so all zeros, or its number itself, because the bit is either 0 or 1. So really the numbers that we'll have to add their binary representations are x0, y0, x1, y0, up to xn minus 1, y0. So these are the bits of the first number. The bits of the second number start from x0, y1, and so on, up to xn minus 1, y1, and so on and so forth. So we'll have a ladder of these numbers. The last of them would be x0, yn minus 1. Well, actually, it would start here in this column, x0, yn minus 1, and so on. So how many numbers we have in total? We have n numbers to add. Each number consists of different number of digits, but what is the highest number of digits in all of them? Well, 2n digits in the largest of the numbers. And by adding them up, we'll get the result. So first we note that getting all these single bits that we have here in this ladder is pretty simple. So these all bits are just conjunctions of the input bits. And so if we are to build a circuit, what we can start with is we can take like all our inputs that we have from x0 through xn minus 1, from y0 through yn minus 1, and we can just make all the pairwise conjunctions simultaneously. So this would be a single layer consisting of many conjunctions. This layer will have size which is proportional to the number of pairs, x times y. So the size of the layer will be theta of n squared. And the depth will actually be 1. So here the depth is constant. Now, after we have all these bits, well, actually we'll also formally need to have zeros, because the last numbers, they are padded with zeros on the right. But we know that to construct a constant 0 or a constant 1, we just take any input of the circuit and we take negation of this input, and then we take conjunction of the inputs with its negation. So thus we have constant 0, or we take disjunction of the inputs with its negation, thus we have constant 1. So it's not a great deal. It does not violate these bounds for our depth and size. So we have all the individual bits in a reasonable size and depth. Now, what do we do with these bits? We add the corresponding numbers given by their binary representations. And so we can employ lots of adders. So we have, after this layer, essentially everything needed to be able to consider our numbers. So we have numbers, let's call these numbers z1 through zn. So these are actually numbers that we need to add to get the result. So we compute the sum of these numbers by, for instance, employing a binary tree structure. So we just take z1 and z2. So let me draw it like this. And we take an adder, which takes these binary representations and produces a binary representation of z1 plus z2. Then we take z3 plus z4, so we kind of join our numbers in pairs, and we compute sums within all these pairs with adders. So after this layer of adders, essentially we have n/2 numbers. Well, ceiling function of that. I will not write down ceiling or floor functions because they do not really influence the asymptotics of size or depth of our circuits here. So each time we now apply this layer of adders, and all the adders work simultaneously in parallel, we reduce the number of numbers which we need to add by 2, by multiplier of 2. And so the number of these layers of adders will be big O of logarithm of n. We have logarithmic depth in terms of the number of adders, but each adder, of course, has its own depth. So the depth of this adder is itself big O of log n. And finally, the depth of our circuit in terms of individual Boolean elements, conjunction, disjunction, and negation, is big O, or in this case it would be more correct to call it theta. So the total depth of our circuit is theta of log n times log n, so log n squared. What about the size? The size of the circuit would be the number of layers times the maximal size of each layer. So this would be the upper bound. So we already have quadratic size here, just the layer of individual computation of the bits. And now we have a linear number of adders, and each adder has size, as we recall, big O of n log n. So the size is theta of n squared times log n. Okay, so this is not bad. And this is also not bad because this is at least polylogarithmic depth. So some polynomial depending on a logarithm of the size of input of our circuit. But we can do even better, and we can switch this square of logarithm to an ordinary logarithm by adding our numbers in slightly different way. So currently we're taking each pair of numbers at a layer and add them into a single number. Then we take these numbers, group them, and produce the next layer, and so on. But now we will do it a bit differently. We'll organize layers that take 3 numbers and then construct 2 numbers out of these 3, so that the sum of all the numbers at the previous layer is equal to sum of all the numbers at the new layer. And this is what we call the 3 to 2 trick. Let's consider 3 m-bit numbers: a0 through am-1, b0 through bm-1, and c0 through cm-1 in binary notation. So what happens when we add these numbers up? When we add each column here 3 bits, the result would be from 0 to 3. And this is what we can write in 2 bits in binary form. So any integer from 0 to 3 actually occupies just 2 bits. And let these bits be, say, D0 and E0. Now we'll write E0 here, And D0, which actually is the higher bit, we'll write here. When we add the bits A1, B1, and C1, again, the result can be written in 2 bits. And these bits we'll call D1 and E1. E1 goes here and D1 goes there. And so on and so forth. Up to this last group of bits, they will produce 2 bits, EM-1 and DM-1. So now we argue that the sum of these numbers in the binary notation is equal to the sum of 3 original numbers. So we can actually express this using just standard algebraic expressions. The sum of these numbers is equal to the sum of 2 to the power of k ak for k equal to from 0 to m-1 plus the sum 2 to the power of k bk plus the sum 2 to the power of k ck, where k ranges from 0 to m-1 everywhere. Now we can combine these sums, of course, into a single sum where we have ak plus bk plus ck here. And now, as we know that this guy can be expressed as 2-digit binary notation, which we call dk and ek, then we can express this sum as a sum of 2 to the power of k times 2 dk, so 2 to the power of k plus 1 dk for k ranging from 0 to m-1, plus the sum of 2 to the power of k ek. And really, these sums are the numbers that are given by these binary representations, this one and this one. So now we can mimic this scheme that transforms 3 numbers into 2, such that the sum of the 2 numbers is equal to the sum of original 3 numbers. And what's great here is that these bits depend only on these 3 input bits. So all these pairs of E's and D's, they can be computed simultaneously in a single layer, which does not add much to our circuit depth. So now let's, instead of combining these numbers Z1 through Zn that we had using this binary tree of adders that allows us to do it with this type of layers, but we have to use logarithmic depth on each of the layer in terms of Boolean elementary operations. We'll still have the logarithmic number of layers, but on each layer we're performing much simpler computation. So we compute simultaneously this pair of bits by using triples of bits. And so we employ a circuit that computes the transformation of A0, AM-1, B0, BM-1, and C0, CM-1 into this E0 through EM-1. And, well, we can have this 0 here as well if we like. It's not a great deal. Or we can start with D0 up to DM-1, because we already know how to get zeros whenever we want. And so these kind of circuits, which we can call 3 to 2, we now employ this circuit to combine our numbers Zn up to Z1. So we now use a layer of these circuits to combine Z1, Z2, and Z3 together into 2 numbers. We combine Z4, Z5, and Z6 into 2 numbers. So here we have this 3 to 2 circuit, and so on and so forth. And we get on the next layer here, we get approximately n times 2 over 3 numbers. So now the number of the layers that we'll have to have like this is of course logarithmic. So the number of these kind of 3 to 2 layers would be logarithm base 3 over 2 of n. Anyway, this would be the logarithmic number of layers. And the depth of each layer is very, very small, because we see that each of these 3 to 2 circuits, it uses just 3 bits, say C0, B0, and A0, to compute E0 and D0. And these computations, they are performed simultaneously for each triple of the input bits. And the depth here is constant. The size of such circuit is linear on M, on the number of inputs. So we see that even though each layer consists of like non-trivial circuits, still they have constant depth, and thus by total logarithmic depth, in terms of the number of basic Boolean operation, conjunction, disjunction, and negation, we reduce all our n numbers into the situation when we can no longer use the 3 to 2 trick. And when cannot we use this? When we are only left with 2 numbers. We do not have even a single triple of numbers to combine. So we have 2 numbers, and in the end we'll have to use at least one adder. So we still have an adder here, but this adder gives us logarithmic depth and the size, which is big O of n log n. So what is the total size and depth of our circuit? The depth, as we now see, is just logarithmic, and the size, what it is determined by. So the size of each 3 to 2 circuit is big O of n in the end, and the number of layers is this one. So the size of the circuit actually is determined by this layer of computing single bits. We cannot get smaller than that, because all the 3 to 2 trick circuits and the last adder that we employ, they have size which is dominated by this square of n, and the depth that we have is produced by these all circuits. So, but it's still logarithmic. So in the end, our depth is logarithmic, our size is quadratic. Now the question is, can we do better with the size? In terms of depth, well, it seems already quite efficient. And later on, we'll discuss some algorithms that improve on the size of the circuit, so that are able to produce a circuit of sub-quadratic size. But that will be a bit later. And next, we'll turn to the last operation that is left, to the division.